of the Women in Logic lecture series. So today, it's a great pleasure for me to have here Laura Kovács.
Sorry. Sorry. Yes, Laura Kovács. Laura Kovács is a full professor of computer science at TU. And she's leading the automated reasoning APRE group of the formal methods in the systems engineering division. Her research focuses on the design and development of new theories, technologies, and tools for program analysis, with a particular focus on automated assertion generation, symbolic summation, computer algebra, and automated theorem proving. She's the co-developer of the Vampire Theorem Prover and a Wallenberg Academy Fellow of Sweden. Her research has also been awarded with an ERC Starting Grant 2014, an ERC Proof of Concept Grant 2018, an ERC Consolidator Grant 2020, and 2 Amazon Research Awards 2020 and 2023. And recently, she received financial support from LEA Frauenfonds to disseminate unplugged computer science to elementary schools while organizing computer science workshops with school children at the TU.
So, Laura, thanks a lot for accepting to be our invited speaker today. So if you have some questions for the talks, just write them on the chat and we will read them after the talk. And you can also upvote the questions that you like more. So those questions will have the priority. And so Laura, you can share your screen and the floor is yours.
So can you see the screen?
Yes.
Great. So yeah, thanks a lot for having me. And the first time actually I give a talk in this initiative. So I chose a topic, and I will give you a bit of explanation why I chose this topic in a while. But it's about automating game theoretic reasoning or game reasoning in blockchain security. And before I just start into the aspect of automated reasoning in blockchain security, so as Josephine said, like my research or my group is working on all aspects of automated reasoning. And in a vague sense, if I'm about to define for you what automated reasoning is, especially in the hype of rising elements of machine learning and artificial intelligence, so this is a very vague but quite generic definition that I apply in my group. So automated reasoning essentially involves 2 tasks. First, you take a mathematical problem, or you take any problem, and you try to represent this problem as some precise knowledge, and the precision we are using in my group is math and logic. And once you have this abstraction from a real-world problem as a mathematical statement, then the next step of automated reasoning, and this is where automation comes into, that we want to provide a computer support to the automatic check whether the statement is true. And my group at TU essentially applies automated reasoning for various areas of system development. Well, in system proving that software systems are safe, proving that software is terminating. We do it recently for synthesizing code from a specification. Do a lot in probabilistic programming and also in cybersecurity. And this is essentially the topic of the group, in a vague sense, doing all aspects of automated reasoning by identifying the niche of automated reasoning in various areas. And to credit, the funding of the group is mainly thanks to the European Research Council, as well to the Austrian Science Funds, Vienna Science and Technology, and Amazon Web Services. And essentially, our results are also driven by real-world use case scenarios in collaboration with Microsoft Research and Certora, which is a smart contract company. It's not anymore a startup, it's already like a consolidated, quite successful company. However, my research is on basic research. So it's about theory, foundations, algorithms, and try to scale it. And as you know, the topic of today is about automated game reasoning in blockchain security. So I will touch upon on various aspects of cybersecurity. Now, I checked also who are the people in the attendees. So I know some experts in security are attending the talk. I'm actually not an expert of cybersecurity, but I have amazing colleagues at TU Wien who are experts in cybersecurity. And together with them, we try to map the problem for cybersecurity into a mathematical or logical statement. And then we are in the world of automated reasoning where we can essentially provide solutions. And this is the reason why I chose this topic, although this topic has been emerging in my group in the past 4 years, essentially. But I thought for a topic in women in logic would be a great choice because for some reason, this topic has been a women-dominated topic in my group, and it's ever since then. In the past 4 years, whoever leaves and joins the group, it's mainly female researchers. So it's really, it's a joint work that I'm going to present together with Sophie Rain. She has been the main drive behind this work, a PhD student in my group, as well as Leah Brucker, who was a master's student with me, Anya Kovács, she is a postdoc in my research group. The only male person is Michael Rawson, who is working with us together with on the vampire theory improving development, and recently together with Ivana Bocheska, we also work together on automating game reasoning in blockchain security. But however, I said we are not really an expert on cybersecurity, so we do collaborate also with two additional experts in cybersecurity from the TU Wien. This is Matteo Maffei and Zeta. I hope she will forgive me that I don't pronounce her name, but she's a tenure-track professor in cryptography at our university. So let me get into the meat, okay? So not give you a bit of, not just giving you a lot of high level, but let me tell you what this work is about. And when we started this work in 2020-21, then essentially people were, this was the hype of, or there was a rise of blockchain technologies, decentralized finance, and all applications of that. And the question of cybersecurity was mainly posed by the fact that, let's say, just think that you have two parties or two users of blockchain, one a provider and one a user. And the question the classical question, I would say, from the security perspective is that you have a provider and you have a user, and the user's worry is about when can a malicious person steal my data? Okay, so I'm going to, let's say, the user, she's going to encrypt, she's going to use some provided encryption mechanisms, encrypt the data is completely anonymized, and then the question, well, is it actually well anonymized? Is it safe? Is it secure? And it turns out that also in the past, there have been quite many use case scenarios where there have been some cryptographic breaches in this chain of technology. So it might be that although the user believes that her data is well encrypted, actually there is data leak happening, so the data can be stolen. And the one classical view in my perspective in terms of cybersecurity is answering the question, can I give you cryptographic guarantees that your data is not stolen, is not leaked? And this is where we have great researchers at TU Wien, and I also have collaborators in this area, but this is not exactly the topic of the talk. Because the topic of the talk is going to work on or going to shed light on a different kind of question. So even assuming that you have cryptographic security by answering this question, okay, so your data is not leaked, there might be some other questions that you want to put up when you're working with blockchain technologies. And one is that, again, you have two parties. And now the question is that the user, or there are two users, and they might actually want to collaborate together because they might maximize, if they collaborate together, they might maximize their winning, or they might maximize their gain. So in the classical setting of cryptographic security, I would say the question is, can a malicious person steal my data? Whereas in this new approach or this new view on security, we also consider some economic questions. Well, is there any incentive for me to share my data? Maybe not entirely, partially, but to the extent that I would collaborate with users. And that's actually what we will define, or how we define game-theoretic security. Okay, so for users acting on the same blockchain or the same decentralized protocols, is there an incentive to work together rather than working alone? So is there an incentive to collaborate? Now, that said, actually, I do work also in cryptographic security, although I'm not going to talk about this in this talk. And we have a great work on proving that what happens that malicious data cannot be leaked on a blockchain, and we have a tool as a follow-up of our vampire theory improver, it is called crypto vampire, and essentially there it comes to the first step of automated reasoning. What problem do you want to formalize? In a case of cryptographic security, I would say the problem you want to formalize essentially should capture properties. For instance, you are using hash functions or uniqueness of hash functions, which are in the cryptographic landscape, are usually expressed using inductive defined data types. So if you're going on that domain, it's quite natural that your problem formalization on math or in logic is going to be in higher order logic with induction. So then what you want to do there, you want to automate by pulling down the higher order perspective into a first order theory of inductively defined data types. And it's actually quite challenging, but it works quite surprisingly well. Yet the talk of today, and again, it's a different formalism, what problem you're tackling. And the security question I'm tackling today is that, is there an incentive to share my data among users of blockchain? And what I'm going to show through the talk that essentially this problem, then formalized properly, can be translated into a first order reasoning problem, essentially a first order theory problem, in the first order theory of arithmetic. And our tool in this respect is called CheckMate. And there are these two complementary views of security. And depending how you address and solve this problem, you are having different kind of expressivity as well and different kind of computability problems. So in the setting of cryptographic security, what we did in Crypto Vampire, you do higher order reasoning by bringing induction in first order theory improving. Whereas in the game-theoretic security, we do so-called SMT solving, satisfiability modular theory solving in the first order theory of arithmetic, which is easier, hard to say, but there are decidability results which show that the red part is highly undecidable and the game-theoretic security essentially is decidable or can become decidable. So let me now tell you how this works. And I understand this is a webinar, but I will still try to put up some questions and try to get a bit of interaction. And the way that you can answer to my questions, either by raising your hand or by just writing yes or no in the chat. So as I said, the question here we are going to answer, okay, what are the economic incentives of users to share data among themselves? And there are various ways to give a good answer for that, but the good answer for this, or the answer we are considering in our work is that if you are acting honestly, what I will define in a moment what honestly means, but if you're not cheating, think like this, then you should not be harmed. So whoever is honest should be rewarded, and you only punish the cheaters. And what does it mean to act honestly on a game in a blockchain protocol? Well, is that the first thing is that, well, you should, so deviating from a protocol describes your course of action that is desired to be maintained. So if you're acting honestly, you should have no incentive or should have no reason to deviate from a protocol because it is not rational. You should be honest with respect to the given specification of the protocol. So that's one way, one aspect of acting honestly. And honest players should not lose, okay? So they, even since they're fulfilling the requirements of the protocol, they should never be harmed. So they should never lose money, or their loss should be minimized. So ultimately, an honest player should never end up losing money or having a negative amount of money when using, let's say, cryptocurrencies. And now we gave fancy names to these two properties, but essentially these two properties capture game-theoretic security in our view. So the fact that honest players or actually any player should not deviate from a protocol, we call it so-called incentive compatibility. Okay, so which incentive compatibility means deviation should not be a rational course of action. And Byzantine fault tolerance is the other property that we essentially capture that honest players are never harmed. So they are never going to be punished. No matter what the other users are doing, even the non-honest players act as they want, but the honest players should never be harmed, no matter what the others are doing. So And that's essentially how we define game-theoretic security. And I will come to this kind of like formalize again one more definition, but you would say that the protocol is game-theoretically secure if incentive compatibility and Byzantine fault tolerance is maintained, or we can prove these two properties. And now what is happening, okay, so you have a developer who is writing a blockchain protocol with intended course of action. This protocol is set to security verification, so sent to developers or engineers to provide or verify it's secure. And I'm not saying that cryptographic security is not needed. Actually, it's a must. So it has to be, although we don't work in cryptographic security, but it's assumed that someone did the cryptographic security verification. And then in addition, what we would provide in our work, that we also provide some game theoretic security. So what are incentive benefits of the economic benefits of the users to act together or alone? And if both of these would be maintained, so both game theoretic security and cryptographic security is maintained, then only then, ideally, should the protocol be deployed in the chain. So let me start, and then actually I use this slide from my PhD student from Sophie, but she has it very nicely animated. So there are quite many words in this title, and I will try to capture the three main topics of this work. So first is about game theory. So I will introduce the game theoretic view of a protocol. Afterwards, I will show you how this game theoretic view of a protocol is mapped together with game theoretic security. And ultimately, since we are coming from automated reasoning, we want to automate everything. And this will be our tool. So let me give you a small example. And this is actually was our starting point. It was in 2021, but it took a while to work out all the details. And the paper has been published at the CSF 2023. So it's a Computer Security Foundation conference. And now I'm taking here, I call it, it's a game. It's a two players game. So we are having player A and player B. And let me explain what this tree that you have visualized here, it's going to do. But this protocol, essentially, it's a very simplified protocol of a real world application, namely of a closing protocol used in Bitcoin. So as I said, we have two players, A and B. And these players act depending what the others are doing. So A's actions are influenced by B's action and the other way around. Then there are various actions happening in this protocol. And these actions are denoted on the edges between the players. So essentially here, if the action CH means that A took action CA and passed the token or the action token to player B. And let me tell you what these actions are denoting. So these actions essentially are capturing how the players interact with each other or don't interact with each other. And one action, and by also taking into account the Bitcoin modeling, the Bitcoin protocol features. So one action, this C_H action, actually denotes, or should intuitively denotes that players work together. So they act together and they act honestly together, which means that if they act along, if you start working with this action, then this action should yield a fair split for each of the players. So this would be the closing collaboratively the channel, or closing collaboratively and honestly the protocol. Now the other action would be like not such a nice action. I mean, a user would still act honestly, but doesn't care of what the other user is doing. So it also only closes so-called unilaterally. So doesn't care what the other user is doing, but is still following the protocol and doesn't consider previous moves. It's like a selfish, honest player. Now the other action, D, well, it's not a nice action because it ignores everything what the other player is doing, and it's also dishonest, tries to cheat or tries to play against the protocol. And it does it so that it acts dishonestly. And since it acts dishonestly, it also kind of tries to play with various profits that are, so whoever chooses action D is going to give various profits for action A and action B, but these profits might not be the same. And then another action is the so-called ignore action, that you ignore everything that has been before done and do nothing. It's somehow similar to skip in programming languages, but it doesn't have such nice behavior as in programming languages because everything before has been ignored, so you might still lose. And then S is the action of so-called, then you sign the protocol, you sign collaboratively the closing protocol of the other player. And the other action, okay, this is the last action. There's only 6 actions in this small protocol that you try to prove the other player, try to close the dishonestly, or you prove that the other player acted dishonestly. So what's happening in this, so essentially you have 2 players in a simplified game theoretic view of this protocol, only 2 players, and each of these players can take an action from these 6 actions. And what we have, so in order to capture the gains or the benefits of actions or the punishments of various actions on the players, each action is going to get utilities or rewards or punished. It depends. These rewards can be also negative. So essentially, if you look at here at the leaves of the tree, essentially saying if player A acted honestly and tries to do collaborative action, but B ignores that honest collaborative action, then everything will be destroyed and player A will get -A reward and player B will get -B reward. Okay? And as you can see now, the leaves of the tree are actually, for each of the player, they are giving you the reward. What are your gains or what are your losses during that course of action? And there are some additional numbers. For instance, there is a fee for closing a channel, or benefit of closing a channel, which I denote by alpha. There is a so-called opportunity cost. So there also closing can cost you a bit, not much, but a bit. And there might be some transaction fee that you also have to consider. So these are the entries of the game. And so I'm not sure how many people are familiar with game theory. Well, I was not familiar with game theory when we started this work, but this is why it fascinated me that essentially you cannot, a game theoretic view of a protocol, you cannot just act alone and care of nothing. So the behavior of the next act, or the outcome of the next action, or the outcome of B's action depends what has been done before, depends what action A did. So when you're trying to understand what are your gains or what are your benefits, then you work with a so-called joint strategy. You take the action of A and you also take the action of B and you combine it in the course of the actions of the game. And what is an honest behavior? Well, if we just say it's an intended scenario, and for this game, I will give you one honest behavior. But before that, let me explain a bit more the actions. I try to explain it briefly, but let me give you a bit more, because so if you don't understand this game 3 and how the actions are tied together, you will not, the talk will be useless to you. So let me just go through now from each action, how it's depicted in the tree. So essentially the first choice A is making. Player A has the first action that it can do, and assuming it chooses CH, so decides to close, so act honestly, but close collaboratively. So it tries to make an effort to get a fair split for both of them, for both A and B, to work together. So A is kind of honest along this line of action, and it passes a token to B. So B gets a kind of an honest token from A, but still B can choose to completely ignore what A did and maximize its own profit, or maybe just act completely maliciously and take all the gains from A away. Or B can also choose, if it's here, well, it can actually choose to follow what A is intended, namely that A wanted to be honest and help player B, and agrees to the help and essentially signs the closing action of A collaboratively with A together. So in that case, both players get the fair split. Okay, so in this case, they played together. So that's it. This is a nicer thing. But A can also choose still to be acting honestly, but only doing her own choice of action. So it closes unilaterally the channel, but it's still honest. However, in this case, so even though it's honest, since A initiated the closing and it did it like a unilateral closing action, well, it still has to wait that the closing times out. So still has to pay the closing fee. And therefore, it's not anymore a fair split because it didn't care what B was doing. Someone has to play this unilateral incentive. So A will get the same split as B, but has to pay the closing the closing fee. And in the bad case, when A is dishonest, so doesn't want to act honestly, then, well, it chooses to be dishonest and passes the token to B. And now B, again, has like two options in this game. Either it ignores, so if it goes in the I action, that completely ignores, but it ignores everything before. A was dishonest before. B ignored the dishonest action of A, so B lost everything it had before. So it lost quite much. Or the other option could be, although A was dishonest, B can try to prove A to be dishonest. And in this case, the funds of A are given to B. So B proved A to be dishonest, so B is rewarded by getting the funds of A, and it has to pay a small transaction fee, but all the funds of A are lost. So now with only 2 players and 6 actions in this tree, there are various outcomes. And now so someone is telling me what is my honest behavior, and now this tree and these actions have been designed such that the names are quite intuitive, because this action C_H stands for closing collaboratively and honestly. However, I decided the joint strategy of this game that I declare to be an honest behavior is the course of action of CH followed by S. And so this is, someone gave you that this is the honest behavior. And someone can give you a different behavior to declare to be honest, but in this game, I'm considering first that this is the course of action which I consider to be an honest behavior for the game. And now here's a question. And now, okay, let's try to see how this interaction goes. So assuming in this game, I have this many actions, and this is my honest behavior. Is there a way to financially harm A, provided A is an honest player? So remember that, just A is honest, so it's going to act along the honest behavior. So A is going to choose the action CH. And now the question, okay, so A did his job, acted honestly, but honest players should never be harmed. So is there a way to harm A? Is there an action for B, which essentially tells you that which action to take? So I see some attendees are saying yes. Okay, I'm trying to read that. So there is a way to financially harm A. Yes, it is. At least some people believe this is true, and I also believe this is, unfortunately, there is a way to financially harm A. And I try to construct and explain the example so that you really see it. So if, for instance, okay, so this would be the honest behavior, CHS. However, B can at this point, so although A closed collaboratively honestly, B at this point may choose to ignore whatever A did. And it will likely harm itself, but it will also harm A itself. Okay, so A lost all the funds. So when A is positive, and actually we consider A to be positive, then all the funds of A will be negative, and an honest player should never enter in the negative funds. So even though A is acting honestly, someone can still harm A. And essentially, therefore, we would say that this strategy in this game, it's not Byzantine fault tolerant, because what we say that about Byzantine fault tolerance is that honest players should never be harmed. Okay, but A is honest, still it's getting harmed. So the game, it's not a Byzantine fault tolerant with respect to this honest strategy. Now, so at least this one question is answered, and there's another question. Okay, from this point, since this is not maintained, you can say, okay, this game along this honest history, it's not game theoretically secure because one of the properties is already violated. Nevertheless, let me ask the second question is that actually, is deviating rational? Or make it more precise? Oh, okay, now I showed you. Is deviating from the honest strategy, is it rational? And okay, I think I saw some answers. So it's a good point that some people say that, of course, it depends on the notion of rationality. But let me point to that essentially. So you should have no incentive to deviate in order to maximize your profit. And I'm trying. Okay, so look at this game here. So A starts an honest strategy, and now it's B's turn. Okay, and does, I mean, of course, it depends whether B is rational or not, but does B have any, if B wants to maximize its profit, does it have an incentive to deviate from the honest behavior? Well, if it will choose E, if it choose the ignore action, then it will lose all its benefits. Also, A will lose, but B will also be in loss. Whereas if it goes along the honest behavior, so if it acts along the honest behavior, then it will get fair split with A. So B only has two choices, and actually, one choice is much worse than the other one because it will lose. It will lead to losing all its funds. So in this case, there is no incentive to deviate from the honest behavior because the honest behavior yields the fair split. So in this case, essentially, for this particular joint strategy, it is incentive compatible. But now it doesn't mean that this game is always Byzantine fault. It's not always Byzantine fault tolerant, or it's always incentive compatible. Whether the game is game theoretically secure, it very much depends. What is your honest behavior? What is the prescribed honest behavior that we are analyzing? And let me just give you another honest behavior to see the answer or see how things can change. So if A would say that, okay, it's about to follow the action H, is it rational for A to deviate from H? And again, rationality meaning about gaining more money. So it's a bit hard to follow all the chats, and let me just give you first the intuition, and then I give you the answer. So if A chooses, if A acts along H, it will have funds which is alpha minus epsilon. And epsilon is a very small positive number, but it's a positive number, which means that if A acts along the H action, it will end up with alpha minus epsilon funds. Whereas if A would go to the closing collaboratively and ask B to sign, that it would only have the alpha funds, which is bigger than alpha minus epsilon. So by comparing arithmetic formulas, actually for A, there is an incentive for deviate because it's much better for A to take this course of action that we discussed before rather than close unilaterally, but honestly. It loses more. So in that case, essentially, if you're considering the game with respect to the strategy H, then this is not incentive compatible. But if you consider it with the actions CHS, then it's incentive compatible. So I hope you got a bit of the intuition what's happening. And I also saw one of the messages in the chat. Indeed, there are 6 actions, and not all the 6 actions are taking it every step of the tree. And why is that? Because with this small tree, we are describing one particular property of closing protocol in Bitcoin. So it doesn't have to be that all actions are taken. But along these actions that can be taken, this would be one valid scenario in the tree. And along that tree, you can answer whether some strategies are Byzantine fault tolerant, incentive compatible, and so on. So what is happening here, and we got this, actually I like this analogy, those who work more on software engineering or formal methods, because as you can see here, that it really depends which strategy you're taking. The answer of incentive compatibility or Byzantine fault tolerance is going to change or may change. So what it's happening, we kind of have a symbolic execution or an automated reasoning engine on games. And we don't essentially take concrete values for alpha or concrete values for A. Rather, we take the symbolic values that try to capture all possible actions, no matter if alpha is 1, 2, 3, 5, and so on. But as long as alpha, let's say, is a positive integer, and epsilon is a small number, we are trying to capture all possible executions of what A can do in the course of H, in the course of CH, and the course of D. And that's very similar to symbolic execution. You don't take concrete values, but you take symbolic constants or symbolic utilities to describe your benefits. So this small game showed you some of the actions you might take in game theoretic security reasoning. And then what we tried, essentially, one of the big burden of protocols is how you model the protocol by a game. And this is together with Sophie, we did it in our CSF 2023 paper. For instance, the closing game of Bitcoin, we really followed the protocol or the protocol description of Bitcoin closing channels. And you model what happens. If takes particular actions, and this is a sequential step of actions. So first A acts, then B, then A, then B, and so on. There are no simultaneous actions. So we started to model that. And well, the closing game is actually quite big. And then we started to still model it. And it was a lot of pain to model that. And this is just about modeling the game. And we ended up with a huge game tree. So quite many nodes and quite many edges and quite many leaves. The proofs hold if you manage to do this huge manual proofs, but it turned out to be quite painful for us. So the next step, what we wanted to do is that, well, we want to automate this. We want to do this game theoretic modeling, provided someone is giving us a game theoretic model of a protocol. We want to analyze the game or the protocol and answer, is it game theoretically secure or not? In this respect, essentially what you have essentially three types of players. So we had two players in the previous game, A and B, but each A and B can be of three kinds. It can be a so-called honest player, and honest player are those that are always acting along the honest history. Then rational players, essentially those are those ones that they want to maximize their benefits. And Byzantine players, they are completely random players. They are unpredictable. They are malicious. You just don't know what they want. So when we put up these two properties that we say that we game theoretically verify or prove, well, incentive compatibility. Let me recall what it means. It essentially tells that honest players should so being an honest player should always be rational. So or behaving honestly should be a rational thing. So you should not be harmed if you're acting honestly, no matter what the other players are doing. And Byzantine fault tolerance also tells you that, well, honest players are never harmed. So essentially, the rational and honest players, it's good for them to work together, and they will always think like this. They will always win together, no matter what the Byzantine player is doing. So we try to prove that also rational players have an incentive to collaborate with honest players, act along honest histories. So when we talk about game theoretic security, with these two properties, essentially we prove that the rational behavior is always honest for a protocol to be game theoretically secure. And this is our definition. Maybe it's not, so it's surely not the most complete definition, but when we say that a protocol is game theoretically secure, it means that honest player satisfies the two above properties. That is, they're never harmed, and it's good to be good to be honest. So, and then our question was, okay, this is a definition, so how can we automate it? So, and So the question is, okay, is there actually an honest behavior that is indentive compatible or Byzantine fault tolerant? But you have a huge game. And the games that I showed you before, even small games, can have different strategies, and different strategies satisfy different kind of properties. So our question then becomes, okay, given a game, is there an honest joint strategy that is incentive compatible and Byzantine fault tolerant? And if you find such a joint strategy, then your game or your protocol is game theoretically secure with respect to that honest joint strategy. When we just did for the closing game, so this was actually together with Leah Brugger during her master thesis, but it turns out that there are trillions of joint strategies. We didn't enumerate all. Actually, it was timeout to enumerate even like a smaller portion of it. But if you just do the math, how many combinations in terms of actions, players, and strategies you have, it turned out that we have like trillions of possibilities. So this actually called for automation. And that was our winning card, because this is what we know how to do automation or logic-based automation. What essentially we did, we took the game, we took all the actions, all the initial constraints, and a particular security property that I showed you before. And instead of enumerating each action one by one, we essentially captured the game-theoretic properties of the protocol using logical constraints. And these logical constraints, we call them SMT constraints, but essentially if you look at the first line of this SMT constraint, it tells that one of the actions has to be taken by one player. But if one player is taking one action, it cannot take the other action. So you have so-called at most one constraint. So, and you can encode it per player, per action, all these properties, and encode them as SMT constraints. And this essentially, these SMT constraints, if you remember in this game, let me just come back shortly here. See, I'm time, but essentially you're in your SMT constraint. Ultimately, when you're solving, you're answering question whether alpha is bigger than alpha minus epsilon, for example. So this SMT constraints are in the first order theory of linear, or actually non-linear arithmetic. Oops. And that's kind of our main result that that we try to push further. That we given a game which is modeled, or given a protocol which is modeled as a game, every action in this game is becoming a Boolean variable. So if the action takes place, then the Boolean variable is 1. If the action doesn't take place, then Boolean variable is 0. And then various actions of the players in the game are modeled as SMT constraints. And the question whether is there an honest joint strategy can be translated whether is there a model that or is the set of SMT constraints satisfiable? If it is, then we found the honest joint strategy. If it's not, there is no honest joint strategy in the game. So here how, for instance, the joint strategy constraint for the modeling of this game would look like. So again, if you see, for instance, the first constraint tells you that action A can take, so player A can take either either action CH, either H or D, but it cannot take both together. Then you also model what is your honest behavior. So the honest behavior is specified to be C, H, and S. So these two action variable has to be true. And then you also say that, well, you want to prove Byzantine fault tolerance. So for all input to the game, the strategy should be Byzantine fault tolerant. So, okay, I'm a bit out of time. But ultimately, once you model this, what in our work this is together with Anya, Leah, Sophie, and Michael, but essentially we proved that if we have a precise modeling of the game by SMT constraints in first order arithmetic, and any model of this SMT constraints gives you an honest joint strategy and vice versa. So if you have an honest joint strategy, you have a model of your SMT formulas. You know what, let me stop. Let me skip this slide, because this was a bit, okay, I skip the details here. And then with this modeling, what you're having essentially take incentive compatibility of Byzantine fault tolerance, model it, add this additional property among your SMT constraints, and then you can answer, is there an honest behavior? Well, the SMT solver will give you yes for incentive compatibility and also gives you the model, or it will tell you, no, it's not Byzantine fault tolerant. I mean, we are not the best software engineers. This doesn't include Michael Rawson in it. And actually, initially, when we first implemented this, it was It was working automatically, but it was quite cumbersome, and there were many things that could be improved. So then we improved together, also having quite much input also from Michael Ross, and then together we went down to just about execution time, but just verifying the closing game of Bitcoin. It already was a huge improvement that it only took us 30 seconds. So remember, the Bitcoin closing protocol has about trillions of strategies. So just going one strategy one by one would take you, no matter how efficient you are, but it would take you a bit more than 30 seconds. So for us, it was initially 30, well, the refinement 30 seconds execution time. And then we speed up with all kind of additional hacks and revise of the even of the programming languages to almost no time or significant low time. And that's what CheckMate can do for you. So if you give CheckMate is our tool for game theoretic security, automated game theoretic security. It takes a game, which essentially someone provides this game as a protocol model, and it translates the game into SMT constraints describing Byzantine fault tolerance and incentive compatibility and other properties of the game, and then asks the SMT solver to decide whether the set of formulas are satisfiable. If it's satisfiable, then your game is game theoretically secure with respect to the security property. If it's not satisfiable, then there's a question of why is it not satisfiable? Is it because we are missing an information, or is it really the case that it's not secure? And then you can improve that. Sorry, let me just. So if it's not fulfilled, that is, it's not satisfiable, we can actually generate your counterexample that tells you what is your attack vector to violate the security property. You can only report this attack vector back, or you can use an attack vector to revise your model to make it secure. So it's a very similar Cigar loop counterexample guided abstraction refinement, but on the game theoretic security world. Yeah, so I think I had a bit more than I planned. So I have more slides than I planned to talk. Let me just show how actually, so this is how you would essentially, if you're interested, go and you can find in our publication, it's recently, very recent this year, EPA publication with the URL of our CheckMate tool. It's available on GitHub, open source. You can download, compile, and experiment with it. And this is essentially just to show how you would write our input format. It's like a JSON input format, but very specific to a game theoretic standard that we came up with. So you define your players, then you put up your initial constraints that epsilon is always positive. Then you put up some so-called property security constraints, which capture incentive compatibility or Byzantine fault tolerance. Then you specify the honest behavior as being the honest history, and then you specify the tree structure of your game. And then you pass it to CheckMate. It knows what the players, what the actions, and then let me just go further. Actually, CheckMate, okay, it's a lot of animation, but this is how the output of CheckMate will tell you. Well, it's practical. So it's and then so practicality, just to tell you here, practicality is about incentive compatibility. And this is how you should interpret the result. So with that, I would essentially try to wrap up. I think it's an exciting field of research. We just scratch the surface, and we only prove game theoretic security by proving incentive compatibility and Byzantine fault tolerance. There are various other properties that one might consider. And ultimately, the crux of the method is it's the first step of automated reasoning. Well, take your game theoretic property, take your protocol, understand what you want to model as a game, and then take the property that you want to prove completely automatically. You can check out the tool there, and there are quite many new features of CheckMate that we are still developing also together with Ivana, going to our strategy extraction, try to scaling up the model by using compositionality and many new cool features. We have so-called precondition generators. So assuming that your model is only has a partial specification, can I make the specification stronger in order to make the security properties valid? And you can also report attack vectors, which tells you how can you violate the protocol, or how you violate the security property. So this is, the title says about game theoretic blockchain security, but essentially it doesn't have to be blockchain. As in any game, whatever game you're using, if you want to answer whether this game has incentive compatibility or Byzantine fault tolerance, you can run CheckMate on that. So input to CheckMate are games. And also this is also what it shows in our experimental results. So we have blockchain protocols. These were our motivating examples. But we have quite many game-theoretic examples from finances. So like game-theoretic use of market entries or other examples. And what is very cool is so-called tic-tac-toe examples, which are known games from tic-tac-toe players. Okay. So let me wrap up because my time is up. I think, I hope I managed to convince you. I think it's super exciting to work on game-theoretic security or game-theoretic view of blockchain security or game-theoretic view of anything, because it's not just about being secure or being safe. It's really, do I have an incentive to comply with prescribed actions? And what we did in our work, essentially, we automated game analysis by proving incentive compatibility and Byzantine fault tolerance, by translating the game reasoning or security reasoning into reasoning over game strategies using symbolic utilities. And at the end, you even get a security proof that your tool is or your protocol is secure or your game is secure. And all this is done using CheckMate, which I hope I convince you that you should go and try it out. And with this, I conclude. I'm happy to take questions.
Hi, Laura. Thanks again for this very, very exciting talk. So are there questions in the chat? Let's have a look. Not yet.
Yes, in the Q&A, there are a few questions. I can read the first one by Mirko. Mirko says, are we always assuming sequential action choosing, or can agents decide simultaneously on their actions?
Yeah, so I kind of answered at one point, of course, because I read the question. So it's sequential actions. It would be nice to go further to simultaneous action, but currently it's sequential.
Okay.
Yeah. Should I read or you read it?
Just go ahead.
Yeah.
So in principle, the order of the players are random and randomly fixed. Okay, and then so someone gives you the game, and once the game is there, then the order of the player's action is fixed. And depending on the order of the player, how actions are, or depending on the order, of course, the benefits may change. So it can be principle you can do completely randomly, but CheckMate compiles with the order that is given in the tree in its input. Okay, and the other two answers were about incentive compatibility, that there was an incentive to deviate. And yeah, the other one is, in the example was indeed there. So there are 3 actions in the running example, but you only discussed 3 for A. And indeed, so this was one way to model that course of action in the protocol of closing. So not all action need to be taken. But in that small example, these 3 actions were allowed to be taken, and the other 3 were in the first choice of A were not allowed to be taken. Right, okay, so Eva wants to answer. The solver did we use? So it's a bit more complex. So we use CheckMate, which does a lot of engineering and transformation of game-theoretic properties into logical formulas in arithmetic. And once we are nicely manage these game-theoretic properties in first arithmetic, then we are using Z3 as an SMT solver to discharge validity or satisfiability of the formulas. And I'm coming to Mirko's question that no, you should not apologize if you missed the point. You did not miss the point, because indeed, there is no actual role of blockchain technologies, except that we have been motivated by blockchain technologies. But at the end, as I showed in the talk, essentially any game theoretic model can be analyzed by CheckMate, and the answers you get in terms of incentive compatibility and Byzantine fault tolerance. So blockchain, it's in a way, it's just an application domain, but it's quite a useful application domain because protocols have all these issues, whether does it make sense to collaborate, act honestly, dishonestly, rationally, Byzantine way. Okay. So if I understand it correctly, running CheckMate on a toy example game you gave us in the slides would give us a counter example showing it's not game theoretical. Yes, so CheckMate would give you a counter example So if it's not game theoretical secure, you can actually extract a counterexample why it's not. And then it's up to you how you use that counterexample, whether you revise your model or not. It's not just on the toy example, actually, it works on quite bigger examples as well. So, okay, there are several categorical versions of game theoretical semantics in the literature, and does any of them fit or can be made to fit your example? So I'm not sure I will answer this properly, but our semantics is about extended form games, and this is the analysis, or this is the setting of games that we are working it. And I think I don't know about the categorical versions of game theoretical semantics, so I would be actually interested to get more details on that. Okay, then how is the tree structure in the automated approach ensured? Are cycles a problem? So we don't really have, we don't have cycles. So we have trees. So we don't, I mean, we don't even have decks, right? So we really have trees, so there is no cycle happening. Unless if you mentioned about the cycle of the iteration of the solving loop, then, so the thing is, like, you take the game, pass the SMT, CheckMate constructs with the formula describing properties of the game. There's no cycle there, there's no loop there, because there's sequential actions, and you pass it to an SMT solver who either proves or discharge, or either proves the SMT constraints or give you a counterexample. And then the only loop, if you may say, then, well, you can run CheckMate once again with a new counterexample, revising your model. Okay, I'm trying to discharge questions. Okay, so it's Mirko's question. Are the actions of the other agents always transparent? In the example showed, agent B can tell when agent A is dishonest. Well, it's sequential, so you know the history, but you don't really always know the future. So therefore, you cannot have this very modular reasoning in your action. So you know what has happened. So what we are doing in the course of actions, we are kind of collecting the history. So A is doing an action, B is doing an action, then A is doing an action. So A sees what happens before its action, but it doesn't know what the next action will be. So as long as history, yes, but it's not about the future. Oh yeah, that's a good one. So sorry, they're all good comments, but can you please clarify limitations of CheckMate? So model size, number of players. Well, size is definitely an issue, and scalability is definitely an issue. And well, I could, oh, sorry. I think I showed very little here, a bit. You know, you can, how many, oh, sorry for that. Oh, I did something. So how many players you can have. So the more players and the more actions you have, the more, it's a combinatorial explosion problem. More players and more actions give you more possible strategies. So definitely, the bigger your model is, the harder the reasoning goes in practice. Theoretically, it should be fine. So I hope. Are there still questions, or did I miss everything?
No, I think the questions are answered.
Yes. So
a new one just sorry, a new one just popped up in the chat. We can make that the last one, and then
yeah. Sorry, I just checked the chat, but I think I didn't. I don't see any answer. Okay, no. So there's one more question, right?
yeah.
Try to understand whether the toy example is secure or not. Moreover, I'm not sure what the meaning of joint honest strategy is in the case of more than 2 players. What guarantees do I get in the real world with your definition of security? Right. So the toy, it's a good, whether toy example is secure or not. Well, in the toy example, let me just go back here, and then I stop. So it is actually, but you know, the question is the toy example with respect to what honest strategy? Okay, there are too many. Okay, so if you take this honest behavior, then even the toy example, in principle, according to our definition, is not game theoretically secure because we already violate Byzantine fault tolerance. But it is secure if you're only interested in incentive compatibility. Which means, if you come back to Byzantine fault tolerance incentive compatibility, let me just come back to the definitions or the intuition. Okay, so in the toy example, deviation from a protocol is not rational along that honest history, but honest players can be harmed. And whether an example toy or not, whether it's game theoretically secure, it always depends what is your precondition. Okay, what is your joint strategy? So what is the course of actions that the players can take? Okay.
Okay.
Thank you.
So if there are no more questions, I would like to thank Laura again for this great talk.
Thanks a lot.
And I would like to recall to everybody that the next seminar will be on the 24th of January, and the next speaker will be Francesca Pogiolesi. So thanks again to Josephine, of course to Laura, and also to Andrea for her great support. And see you, all of you, in January. Bye.
Bye.
Bye, everyone. And yeah, thanks again, Laura, for the great talk.
Wow.
I
can leave, right? Just to be sure.
Yes, you can leave.
Yes.
Okay, thanks a lot.
Ciao.
Bye.
Yes. Bye, everyone.
Thanks.